Okay, so we're gonna go ahead and we'll get started. Um, so I set up all my teddy bears and put them up, and I'm gonna pretend they're all you guys, and I'll be talking to, I guess, my stuffed animals, right? Um, so we're all here now, unfortunately, on this online class, online video because of the Hurricane Hermine. A lot of you were surprised by that. You said Hurricane Hermine. I thought it was Hurricane Hermione. So did I, until I, looked up all the spelling, and nope, it's not, which sucks. I was outside waving my wand, pretending I was, tearing down palm trees and, causing car crashes. Nope. Thanks a lot, Voldemort. Anyways, uh, so unfortunately we're here and it sounds good. All these things are happening and we get to miss class, and that sounds great. The reality is it's not, because now you're stuck watching this 2.5 hour video, and now I'm stuck giving this 2.5 hour video instead of going through all this work. But that's okay. So last class, we talked a little bit about, we finished chapter 1 as the first class we ever met, and then we started chapter 2 just a little bit. So I'm going to go back and do a little bit of review for chapter 2 at least. So remember, this here is an atom, and we talked about the different subatomic particles, the different small pieces of an atom. There's a proton and a neutron and an electron. This pink one here is a proton, and it's not labeled, but I'm not guessing because I know protons have a positive charge. So protons are positive, and they're also found in the nucleus. This brown thing here, it's not labeled. So from that, I can guess, well, that's a neutron because it doesn't have a charge and it's found in the nucleus. So protons and neutrons are found in the nucleus. And then electrons, that their charge is negative. So protons are positive, neutrons are neutral, electrons are negative. And electrons are found in this outer region, which is shown really well here, known as the electron cloud. So then we introduce these really complex terms that they're really important to understand, though, and people always get confused. There's an atomic number and an atomic mass. The atomic number tells you the number of protons in the element's nucleus. It only tells you the number of protons. And the thing is, this number is really special because it's unique for each element. It determines the element's identity, and that's a really, really important point. Then there's the atomic mass or mass number, which are almost, used synonymously, and they just tell you the number of protons and neutrons. And this is a really, really important point. You really need to know the difference between these terms because they often get confused. And some people, they go to the test and you don't want to think, oh, atomic number tells me the number of protons and neutrons. You're going to start racking up the questions, which you get wrong, and you don't want to do that. So I said before, the atomic number tells you the element's identity. The atomic number here for this element is 2. That means this element has 2 protons. Any element that has 2 protons, we always call helium. Helium will always have 2 protons, and the only way you can call something a helium is if it has 2 protons. If it has 3 protons, it's not a helium, it's a lithium. If it has 4 protons, it's not a lithium or a helium, it's something else. So you want to make sure you understand that. That's a really, really important point. Then there's the atomic mass, which tells you the total number of protons and neutrons. The total number. So here, the atomic mass is 4. That means it has a combination of 4 protons and neutrons. And you can tell here, well, since there's 2 protons, that must mean there must be 2 protons and 2 neutrons here. That's a really important point to kind of understand that. On the test and on the exams and quizzes, I'll give you a periodic table if needed. Most likely I'll just give you the little bits of information which you need to know. So we said before, the atomic number determines the element's identity. This is a carbon because it has 6 protons. All elements that have 6 protons, or all atoms that have 6 protons, we always call a carbon. If an element has 7 protons, we'll always call it a nitrogen. If an element has 8 protons, we'll always call it an oxygen. And that's a really, really important point. We always, always, always do that. A nitrogen can never have 8 protons. No. The definition of 8 protons is oxygen. This is a slight new slide that I put in to try to, put some of these things I'm saying verbally into physical words. So these elements on the periodic table, they all have a neutral charge. That's a really important point. They all have a neutral charge. And for an element to have a neutral charge, that means you have to have an equal number of positive and negative charges, or an equal number of protons and electrons. So you look at this, and let's just go to carbon. Carbon has 6 protons. So carbon also has 6 positive charges because of that. So for it to be neutral, it has to have 6 negative charges, or 6 electrons. So for all these things here in the periodic table, oxygen is 8 protons, so the periodic table version of oxygen is going to have 8 electrons. Argon has 18 protons. The periodic table version is going to also have 18 electrons. So if you know the atomic number, it tells you the number of protons in the nucleus, and also it tells you how many electrons are in a neutral atom, like we just said. Then there's something called an atomic mass, and the atomic mass tells you the number of protons and neutrons. Now, since you already knew the atomic number, the number of protons, then you can do a subtraction problem and then figure out the number of neutrons. Here's a really cool example. So zinc has an atomic number of 30. That means zinc has 30 protons. All elements on a periodic table are neutral. So if it has 30 positive protons, there has to be 30 negative electrons. And then the atomic mass is 65.38. Let's just call that 65. And then we look and we say, okay, zinc has 65 protons and neutrons total. And if we know it has 30 protons, we can subtract, and then we find out it has 35 neutrons. Because 30 plus 35 here forms 65. And that tells you the total number of protons and neutrons. And now we know the electrons. So now we know everything we kind of need to know about this element. So that's really important. You can kind of do these calculations. And you won't get a calculator on the exam. So it'll be easier math. Kind of like this, kind of simple math. We also said before that these elements can differ in the number of neutrons. And the ones that do that, we call them isotopes. So isotopes are elements that differ in the number of neutrons. So it doesn't always have to have the same number of neutrons. In this example, zinc has 35 neutrons. Zinc also might have a different zinc, an isotope of zinc, might have 34. An isotope of zinc might have 36. An isotope of zinc might have 37. These are just elements, the same element, but they differ in the number of neutrons. Then there, like we said last class, there are radioactive kinds which decay spontaneously. They give off particles and energy, and they're unstable. This can be good because it allows us to do imaging like the PET scan or the PET scan to view cancer and view other things. We said before these electrons have something known as potential energy because of where they're located. And we call where they're located kind of the energy level or the electron shell. The farther it is away, the more energy it has, like we said last class. So the electrons in the outer shell, which we said was called the valence shell, those are the ones that have the most energy. So valence electrons are the electrons in the outermost shell, the valence shell. These are the most important electrons because they determine how an element or how an atom interacts with others and how it behaves chemically. We said last class there's an octet rule. Oct means 8. There's an octagon. An octagon has 8 sides. The octet rule says generally most elements want to have 8 valence electrons. And if they have 8, we consider it full and it is the most stable state. So all things want to try to get 8 valence electrons, unless they don't follow this rule, but most do. That's why we says generally. If it has a full shell, they're relatively non-reactive because they're so stable. And they're called noble gases. Noble gases are unreactive elements. They're inert. They don't react with other things. They kind of just sit there. Because they have a full shell a full valence shell, they have a full set of 8 electrons. They want 8. They have 8. There's no reason to take some. There's no reason to leave some. It has exactly what it wants, so it's just going to chillax. And that's a really important point. What the heck are valence electrons? What's the octet rule? So this is a nice periodic table here that shows you these are all noble gases. And all of these here have a full set of 8 valence electrons, except helium. It's a little weird, but they want to have 8 valence electrons, and they do. That's why we call them noble gases. They don't really interact much. They're noble gases. Like we said, not elements follow this. It's not technically a law. It's just this rule. It's this guidelines. Most follow it. Some don't. Like, here are some exceptions. These aren't too important, but the important ones, I guess, are hydrogen and helium. They don't really follow that rule. In fact, they're the most stable state when they have a full shell of 2, which kind of shows you here. This inner shell is full with just 2, because that's all they need there. And you see here, these have the 8 valence electrons. 2, 4, 6, and 8 valence electrons, so these are known as noble gases. So if an atom doesn't have a complete valence shell, if they have 6 valence electrons, if they have 7, if they have 1, then they're going to interact, and they're going to try to satisfy this octet rule. They want to have 8, and they're going to see, what can I do to get 8? I'm going to take some, I'm going to share some, I'm going to lose some, I'm going to do something to do that. And when they do that, they do this thing called a chemical bond. They make this interaction or attraction between atoms that have incomplete valence shell. They do this to attempt to satisfy the octet rule. So here's a really important bond known as the ionic bond. An ionic bond involves the transfer of a valence electron from one atom to another. So one atom gives up an electron and the other one takes it and accepts it. So it involves a donor and an acceptor. So here's one of the best examples of an ionic bond. It happens between sodium and chlorine. So sodium gives up an electron and it goes to chlorine. Sodium gave up a negative electron. That's going to change the charge of sodium, like we're going to find out. This is really, really important, though, to see what the heck is an ionic bond. It's when a valence electron is transferred from one atom to another. So once you give up an electron, there's going to be a difference in charges. You gave up something negative. Now that thing now has less negative, so it's positive. And that thing before that was a neutral accepted a negative electron. Now there's more negative in it, so it's actually a negative atom. We call these ions. Ions are charged atoms or charged molecules. They have a different number of protons and electrons. Remember, the periodic table doesn't involve ions. They're all neutral. They have the same number of protons and electrons. But when you start changing the electron number, then all of a sudden you form an ion. So it could be positively charged, like a cation, or it could be negatively charged, like an anion. So these two things, a cation and an anion, they're going to interact and they're going to form an ionic bond. So this is really, really important to understand this terminology. What the heck is an ion? And then that makes a positive and negatively charged ion. A positively charged one known as a cation, and a negatively charged one is known as an anion. The way a lot of people remember that is the cation has a T in it. And that T, I don't know about you, but looks awfully similar to a plus symbol. And plus and positive, and so forth. So here's just that example one more time, but now it makes a little more sense. So sodium has 11 protons and 11 electrons. Chlorine has 17 protons and 17 electrons. You can find this by looking at the periodic table. These are the atomic numbers. And they're all neutral, so they have this. So now if you look, how many valence electrons are in sodium? 1. That's it. So sodium only has 1 valence electron, and chlorine has 2, 4, 6, 7. So chlorine wants to get 8, sodium wants to get 8, so they think, how can we do this? So they form this interaction, they form this ionic bond. Now, sodium gives up an electron to chlorine. Chlorine takes the electron. Sodium now has a complete valence shell. Look at this. 2, 4, 6, 8. Chlorine now has a complete valence shell. 2, 4, 6, 8. Sodium gave up an electron, so now there's more positive protons than negative electrons. Sodium now has a positive charge. Chlorine accepted an electron. Now there are more negative electrons than positive protons, so it has a negative charge. If you're a positive ion, you're referred to as a cation. If you have a negative ion, you're referred to as an anion. So throughout this chapter, and I think a couple more chapters in this book, I have these really cool animations, and they're nice, and you can look at those on your own time, which is what you usually do, if you like. But they kind of describe it, but in this, monotone computer, Siri voice. So these ionic bonds form salts, or ionic compounds. These are formed by ionic bonds, like sodium chloride here, a table salt. So we said before, elements want to follow the octet rule. They want to have 8 valence electrons. Sodium wants to do it, but here's sodium. It only has 1 valence electron. So it thinks, how can I get to 8? I could gain 7, but it's lazy like you and I, and that's a lot of work. Or it could lose 1. Now a lot of you are saying, but 1 valence electron minus 1 electron is 0. And you are correct, but if you look at this, here's the outer shell. If you lose that electron, then you just go to the next shell, kind of like we saw here. You lose this outer shell, and now you're just left with this shell becomes the outer shell, and there's 8 electrons here. So sodium could either gain 7 or lose 1, and losing 1 just makes more sense than gaining 7. So it does that. Chlorine wants to satisfy the octet rule. It has 7 valence electrons. It could gain 1, or it could lose 7. Gaining 1 makes a little more sense to me, if you ask me. So that was ionic bonds. Those are where electrons are transferred from one atom to another, and they form salts. Then there's something known as a covalent bond. And a covalent bond is where electrons, they're not transferred, they're shared. Someone doesn't give it up and the other one takes it. One becomes positive, one becomes negative. There's an ion and a cation and an anion. That's not the case here. With a covalent bond, electrons are shared. Now, isn't that nice? They share the electrons, and when they do, it counts for both atoms' valence shell. So let's just say, this really doesn't happen, but let's just say one atom has 4 valence electrons. Then it might interact with another atom that has 4 valence electrons. They share those 4, and together they have 8 electrons. Each one only has 4, but they're sharing each of their 4, so they're sharing 8 electrons total, so they both have 8. But there's only a total of 8 electrons, not the 16 that you would think that the two should have. They just share 8 between them. So that's just an example of a covalent bond where electrons are shared. Covalent bonds can be formed between atoms of the same element, like hydrogen and a hydrogen, or between different elements, like a hydrogen and an oxygen, like what happens in water. And remember, a compound, which we've already introduced, is a substance that has two or more different elements. So a compound has two or more different elements, like water, hydrogen, and oxygen. But oxygen gas, O2, two oxygens put together, is not a compound because they're not different elements, they're actually the same element. That's a really important point, though, to note. What the heck is a covalent bond? They share electrons. So here's a really cool picture of this. Here's a hydrogen atom. They each have one electron. They don't follow the octet rule. They're the only exception, one of the few exceptions, and they have one valence electron, but they want to have two. They then say, well, let's form a covalent bond. Let's get close and let's interact and let's share. I have one electron. You have one electron. Let's share. So now, each one is one electron. They share, and now they each have two electrons together. They only have one each, but they're sharing two, so they both share and complete their valence shell. So when you do this, you share electrons with covalent bonds. You could share one pair of electrons, and you form this. Whenever you do that, you write it out as one line here. You share one pair of valence electrons, aka two total are shared. Or there could be a double bond, or a double covalent bond, where you share two pairs of valence electrons. Two pairs, that means four total valence electrons. And remember, these covalent bonds, they form molecules. So covalent bonds form molecules, while ionic bonds, they don't form molecules, they form salts or ionic compounds. So here's an example. Hydrogen and hydrogen, they share one pair of electrons. They share two total. So they then complete their valence shell. It's complete. Oxygen here does a double covalent bond. They share two pairs of electrons, aka four in total. So here there's 2 electrons, 4 electrons, 6 electrons, and then 8 electrons. This one has 2, 4, 6, 8. They both have 8 electrons. They share between them. They only share 4 total electrons, but they now share enough so that they each have that complete valence shell. They satisfy that octet rule. So just here are some pictures of these different molecules and how they can interact. Hydrogen, oxygen, methane, and how they interact. So some of them can be really complex like this, but if you look, they all satisfy the octet rule. So with covalent bonds, electrons are shared. The reality is, electrons, they're not always shared equally. That sounds good, that, we'll switch off. You'll have it 50% of the time, I'll have it 50% of the time. That sounds kind of good. Or maybe you're one of those compromise things, with your divorced husband, and you're like, okay, we'll share our kids, but we're both going to drive halfway. So maybe those electrons you want to think are found, halfway in between both atoms when they share it. That sounds good. The reality is, a lot of times that's not the case. A lot of times, they're not equally shared. So when they're not equally shared, we call it a polar molecule. Polar molecules are when those electrons are not evenly shared. So that's a really important point. Polar molecules are when electrons aren't evenly shared. As a result, you're going to produce a partial negative charge and a partial positive charge. And you look down here, and you'll see why. So here's oxygen and hydrogen, H2O. That's water. Here are the electrons. If it were me, I'd say, well, I think the electrons should be here. That's about the halfway mark, They each should drive 1 mile, to meet up. Or they each should, halfway. That sounds good. That's not the case. Oxygen is greedy. Oxygen likes electrons. So it's going to pull these electrons in, closer to it. So this is more like a 90-10 relationship here, right? most of these electrons are on the oxygen. As a result, for what we know about electrons, your brain should be, rapidly firing right now and saying, okay, what charge are electrons again? Electrons are negative. So you're telling me these negative electrons are closer to the oxygen. That means that the oxygen should be a little bit negative. So we call it partially negative. There's less negative stuff next to these hydrogens. So it's going to be a little positive. We'll call that a partial positive charge. So these are negative and positive now. Not fully negative, they're just partially. This sounds like, why are you telling me all these minute details? If it's not fully negative, don't say it at all. If it's kind of this, kind of that, don't be wishy-washy with me. And I get it. But it's really important. We're going to find out because that's why water has all these really awesome properties that allow it to be sustainable to our life and allow it to do some really cool things. So it allows for something called hydrogen bonds. You have the negative oxygen and the positive hydrogen because of what we said here. Negatives and positives, even if they're partial, they're going to interact and attract. So this negative is going to try to form up with that positive, and this negative, and that positive, and this negative, and that positive, and this negative, and that positive. So it's going to form these weak attractions. These are known as hydrogen bonds. Hydrogen bonds are the weak attractions that occur between a partially positive hydrogen and a partially negative element. Oftentimes it's oxygen, not always, but a lot of times it is. In this case here, it's oxygen. So these all line up, and then something still lines up with these, so you're going to form this, huge, kind of like snowflake-like structure of all these water molecules interacting with a lot of other ones. It's not just one, it's one molecule in this case is interacting with 4 others, and this one is interacting with 4 others, and this one's 4 others, so it's going to form this kind of like network and this branch, this lattice, almost like a snowflake structure. And that's because of these weak interactions, because oxygen's, greedy. So these electrons are going to be more near oxygen, giving that partially negative charge, and that's going to play a role in bonds and how things are changed and how these atoms interact, these molecules interact. So this is a really good review slide for what we kind of just said. There's a covalent bond where electrons are shared. Then there's an ionic bond where electrons are transferred. In ionic bonds, one atom gives up an electron, one accepts an electron. That's going to cause different electrical charges, and we're going to produce an ion, a cation or an anion. Ionic bonds produce salts. Covalent bonds share, and they produce molecules, and that's a really, really important point to understand. Which ones share, which ones transfer, which one will cause, ions, which one, doesn't, and so forth. So now we're going to get into this, just very briefly, because we have to talk about it. There's something known as a chemical reaction, and that's when you make and break chemical bonds between different elements or atoms. So it's kind of obvious, and you've heard all these things before, but there's a reactant and there's a product. The product is the final piece. The reactant are the things that you put together, and then you form the final piece. So you have to break these bonds between hydrogen and oxygen and then reform them in a different way. That's a chemical reaction, and it produces a product. So I think right now we're going to take a small break, and I'm going to upload a different video. So that was the end of part 1, and now we're going to move on to part 2. Have to do this. That way you can kind of break it up, and you can kind of take this in pieces if you like. And also that way I don't have a 10 terabyte video to upload onto Canvas. That'll get me in trouble. So we'll take a small break, and then you can come back and watch the part 2 of this video.